Download this code from codegive.com, link in the description below. Asynchronous execution in Rust, Advanced Part 5, Channels, Mutexes, and Shared State. This tutorial builds upon the previous parts of our asynchronous Rust journey. We'll delve into handling shared state in asynchronous contexts, specifically focusing on using channels to communicate between tasks and synchronization primitives like mutex to protect shared data. Recap of previous parts, briefly. Part 1 Introduction to async/await, futures, and async blocks. Part 2 task spawning with Tokio spawn and concurrent execution. Part 3 timers and delays using Tokio time sleep. Part 4 error handling with result and, in asynchronous functions. Part 5, channels and shared state. Asynchronous programming often involves multiple tasks running concurrently, needing to communicate and share data. This is where channels and synchronization primitives become crucial. Without proper mechanisms, race conditions and data corruption can occur. 1. Channels, communicating between tasks. Channels provide a safe and efficient way for asynchronous tasks to send and receive data. Rust standard library offers MPSC, multiple producer, single consumer, channels, but Tokio provides optimized versions designed for asynchronous environments. We will use Tokio Sync MPSC, which is an implementation of the multi-producer, single consumer channel. Key concepts Asterisk sender, TX the sending end of the channel. Multiple senders can exist. Receiver, RX the receiving end of the channel. Only one receiver can exist. Message the data being transmitted through the channel. It must be send and sync, thread safe. Blocking versus non-blocking. Channels can be either blocking or non-blocking. Tokio's channels are typically non-blocking in asynchronous contexts, they return immediately if the operation cannot be completed. Code example, simple channel communication. Explanation 1 MPSC channel string, 10, creates a channel that can transmit string messages. The 10 is the channel's buffer capacity. A larger buffer can improve performance, but it also consumes more memory. 2 tx.send, message, .await sends a message through the channel. The .await makes this a non-blocking operation. If the channel is full, the send will return an error, typically when the receiver has dropped. 3 rx.req, .await receives a message from the channel. The .await makes this a non-blocking operation. If the channel is empty and all senders have been dropped, req will return none, signaling the end of the communication. For error handling we use if let err, equals tx.send, message, .await to handle potential sending errors. This is crucial because if the receiver has been dropped, example due to an error or program termination, sending will fail. 5 While let sum, message, equals rx.req, .await this loop continuously receives messages from the channel until the channel is closed, all senders are dropped, and there are no more messages in the buffer. Important considerations with channels buffer capacity choosing the right buffer capacity is crucial. A small buffer can lead to senders blocking, if the receiver is slow, while a large buffer can consume excessive memory. Consider the expected rate of message production and consumption. Channel closure when all senders associated with a channel are dropped, the channel is considered closed. The req method on the receiver will return none when the channel is closed and there are no more messages in the buffer. Asterisk ownership. Asterisk channels transfer ownership of the data being sent. The sender moves the message into the channel, and the receiver moves the message out. This ensures data safety. Asterisk error handling. Asterisk always handle potential errors when sending and receiving messages. Channels can fail if the receiver is dropped or if the channel is full, if the buffer is limited. 2. Shared state with mutex, and alternatives. When multiple asynchronous tasks need to access and modify the same data, you need a way to synchronize access to prevent race conditions and data corruption. Tokio sync mutex is a common tool for this. Key concepts. Asterisk mutual exclusion. A mutex ensures that only one task can access the protected data at any given time. Locking. To access the protected data, a task must first acquire the lock using .lock.await. This will block the task, asynchronously, until the lock is available. Unlocking. When the task is finished accessing the data, it must release the lock. The lock is automatically released when the mutex guard, returned by .lock.await, goes out of scope. Code example, using mutex for shared counter. Explanation. 1 arc new, mutex new, 0, creates a mutex containing an integer, initialized to 0. Arc, atomic reference counted, is used to allow multiple tasks to share ownership of the mutex. The arc ensures the mutex lives as long as there's at least one reference to it. 2 arc clone, and counter, clones the arc to create a new reference to the same mutex. Each task gets its own arc pointing to the same underlying mutex. 3 counter _clone .lock.await asynchronously acquires the lock on the mutex. This will block the task, asynchronously, until the lock is available. The .await is crucial for asynchronous contexts. 4 guard plus equals 1 accesses and modifies the data protected by the mutex. The guard, of type mutex guard, provides exclusive access to the data while the lock is held. 5 automatic unlock *. The lock is automatically released when the guard variable goes out of scope. This is a crucial feature of mutex that prevents accidental deadlocks. 6 sleep, duration from _secs, to, .await, this is a rudimentary way to wait for the tasks to finish. In a real application, you would use a more reliable method, such as Tokio task join set. Important considerations with mutex *. Deadlocks *. Be very careful to avoid deadlocks. Deadlocks occur when 2 or more tasks are blocked indefinitely, waiting for each other to release a lock. Avoid holding multiple locks simultaneously. Contention *. High contention, many tasks trying to acquire the lock at the same time, can negatively impact performance. Consider alternative synchronization strategies if contention is a significant concern. Fairness mutex does not guarantee fairness. A task that has been waiting for the lock for a long time might not be the next one to acquire it. Arc always use arc when you need to share a mutex across multiple tasks. Arc manages the lifetime of the mutex and ensures that it is not dropped prematurely. Async aware mutex use Tokio sync mutex instead of std sync mutex in asynchronous contexts. Tokio sync mutex is designed to work with asynchronous tasks and avoids blocking the underlying thread. Alternatives to mutex *. While mutex is a common solution for shared state, there are other alternatives that might be more appropriate in certain scenarios. Atomic types for simple operations like incrementing a counter, atomic types, example std sync atomic usize, can be much more efficient than mutex. Atomic operations are guaranteed to be thread safe without requiring locks. Explanation asterisk. Atomic usize new, 0, creates an atomic unsigned integer, initialized to 0. Fetch underscore add, 1, ordering seq cst, atomically increments the counter by 1. Ordering seq cst is the strongest memory ordering and guarantees sequential consistency. All threads see the same order of operations. Load, ordering seq cst, atomically reads the value of the counter. *rw lock *rw lock, read-write lock, allows multiple readers or a single writer to access the data. This can be more efficient than mutex if read operations are much more frequent than write operations. *message passing, channels in some cases, instead of sharing state directly, you can use channels to pass ownership of the data or updates to the data between tasks. This can simplify synchronization logic and reduce the risk of race conditions. Actors are a concurrency model where each actor is an independent entity that communicates with other actors through messages. This approach can be useful for building highly concurrent and resilient systems. The Actix crate provides a powerful actor framework for Rust. Tokio sync broadcast, this allows sending the same data to multiple receivers simultaneously. This is useful when you need to notify many tasks about an event. 3. Combining channels and mutexes. Channels and mutexes can be used together to implement complex communication patterns. For example, you can use a channel to signal that shared data has been updated and needs to be reread. Code example, using a channel to signal data updates. Explanation asterisk. 1 shared data asterisk. The data is a string wrapped in a mutex and an arc for shared access. 2 update signal channel asterisk. The MPSC channel, 10, creates a channel that transmits empty tuples. The purpose of this channel is simply to signal that an event has occurred, the data has been updated, not to transmit any actual data. 3 writer task asterisk. The writer task acquires the lock, updates the data, and then sends a signal through the channel using tx.send.await. 4 reader task asterisk. The reader task continuously listens for signals from the channel using rx.reqv.await. When it receives a signal, it acquires the lock, reads the data, and then releases the lock. Advantages of this pattern asterisk. Decoupling asterisk. The writer and reader tasks are decoupled. The writer doesn't need to know anything about the reader, and vice versa. Flexibility asterisk. You can easily add more readers without modifying the writer. Efficient notification asterisk. The channel provides an efficient way to notify the reader when the data has been updated. The reader doesn't need to constantly poll the data to check for changes. 4. Pitfalls and best practices. Avoid blocking the async runtime. Never perform blocking operations, example blocking I/O or long-running CPU-bound calculations, directly within an asynchronous task. This will block the entire Tokio runtime. Use Tokio task spawn _blocking to offload blocking operations to a separate thread pool. Minimize lock holding time. Hold locks for as short a time as possible to minimize contention and improve performance. Avoid performing lengthy operations while holding a lock. Choose the right synchronization primitive. Select the most appropriate synchronization primitive for the task at hand. Mutex is a general-purpose solution, but atomic types, RW lock, or message passing might be more efficient in certain scenarios. Handle errors carefully. Always handle potential errors when using channels and mutexes. Unhandled errors can lead to deadlocks, data corruption, or program crashes. Use Tokio task join set or Tokio select, For waiting * when spawning multiple tasks, don't use sleep to wait for their completion. Employ Tokio task join set or Tokio select, for more robust and efficient task management and error handling. Join set allows you to await the completion of multiple tasks, and it aggregates any errors they might return. Tokio select lets you wait on multiple futures simultaneously and react to the first one that completes. Testing thoroughly test your asynchronous code to ensure that it is free of race conditions and deadlocks. Use tools like Loom to simulate concurrent execution and detect potential issues. Conclusion. This tutorial has explored the fundamentals of using channels and mutexes to manage shared state in asynchronous Rust programs. Channels provide a safe and efficient way to communicate between tasks, while mutex, and its alternatives, ensure synchronized access to shared data. By understanding these concepts and following best practices, you can build robust, concurrent, and efficient asynchronous applications in Rust. Remember to always prioritize data safety and carefully consider the performance implications of your synchronization choices. Experiment with the code examples and explore the Tokio documentation to deepen your understanding of these powerful tools. Good luck.